Good afternoon, and welcome to my presentation on the evolution of 3D graphics. My name is Matthew Gallagher, and over the next several minutes, I'm going to take you through how the software innovations, from early wireframe rendering techniques to today's powerful GPU-driven pipelines, transformed how we visualize, design, and simulate the world. 3D graphics play a critical role in how we experience the digital world today. They power everything from entertainment we enjoy on the big screen and video games many enjoy, to architectural visualization tools and medical imaging. At its core, 3D graphics are about transforming numerical representations of real world concepts into something humans can intuitively understand and share. But what makes them special in software engineering is the sheer complexity and efficiency that is required even to make the simplest graphics we see today. Real-time rendering requires layers of different software and hardware components functioning seamlessly. In short, 3D graphics represent the culmination of the art, mathematical, and engineering disciplines. The history of 3D graphics began in the 1960s with Sketchpad, developed by Ivan Sutherland at MIT. It was the first program that allowed users to interact with graphical objects on a computer screen. Everything was vector based, but it established key principles which are still fundamentally important today: hierarchical object representation, constraint based editing, and real time feedback. A few years later, computer aided design, or CAD, as many have come to know it by, took off. Engineers can now model real-world objects like vehicles and houses in 3 dimensions. Though the graphics were limited to wireframes, they laid the foundation for object-based modeling, coordinate transformations, and scene hierarchies. Seen here is the Utah Teapot, widely known to be one of the standard reference objects in the early days of testing and experimenting in 3D development. Created by Martin Newman at the University of Utah, it was one of the first objects to be modeled using Bezier curves rather than precisely measured vertices. In the early days of computer graphics, everything was done purely in generalized software. There were no GPUs or specialized hardware, just the CPU running code to calculate every vertex, edge, and pixel. Rendering a single 3D image required thousands of matrix operations. The software had to transform 3D coordinates into 2D screen positions, apply rotations, scaling, and perspective, and then draw each line and surface 1 pixel at a time. Because there was no hardware acceleration, even simple models took significant processing time, which is why early graphics were almost always wireframes. To make this process more manageable, standards like GKS and PHIGS were developed to provide consistent programming interfaces for 3D graphics. These early APIs represented the first major step in structuring graphics through software engineering. The 1980s were revolutionary because raster displays, screens made up of pixels instead of vectors, became the new standard. Unlike vector displays that drew lines, raster displays allowed filled surfaces and shaded images. These enabled shading algorithms, which simulated how light interacts with curved surfaces. Suddenly, 3D models could look smooth and realistic instead of flat and geometric. By the 1990s, 3D graphics entered the mainstream of software development. 2 major software frameworks defined the era: OpenGL and Direct3D, which later became DirectX. OpenGL, created by SGI in 1992, standardized how software accessed graphics hardware across platforms. Direct3D, introduced by Microsoft, brought similar capabilities to Windows. For the first time, developers didn't need to hand code every rendering routine. They could rely on these APIs to handle low-level details like rasterization and memory management. This abstraction was a huge step in software engineering. It separated what you wanted to draw from how it was drawn. Around the early 2000s, 3D graphics underwent another transformation as computation moved from the CPU to the GPU. The GPU was designed specifically to perform large amounts of mathematical operations in parallel, perfect for rendering thousands of polygons per frame. Software engineers adapted by writing shaders, tiny programs that ran directly on the GPU. These controlled lighting, color, and even simulated geometry based effects. This new programming model made 3D rendering more flexible and customizable, but also more complex. Developers now had to think in parallel and optimize performance in ways that traditional CPU code never required. This tight software hardware relationship remains at the core of real time rendering today. Shortly thereafter, the focus shifted from raw graphics code to game engines. These were software development environments that were built for the sole purpose of building 3D experiences with the specific and predefined functionality for graphics, physics, audio, and logic. Engines like Unreal and Unity let developers create entire worlds without needing to code every detail of rendering or input. This reflected a major software engineering milestone, moving from low-level optimization to high-level abstraction and modularity. Engines implemented concepts like component-based architecture, scripting systems, and editor tooling. They also introduced standardized pipelines for importing assets, memory management, and building user interfaces. Game engines changed the entire 3D space. No longer was it the development of 3D graphics a skill possessed by the highly skilled, but rather can be approached by more novice engineers, allowing for a technical boom of the 3D systems. 3D graphics soon escaped the confines of gaming. Architects began designing and visualizing buildings interactively. Surgeons could use 3D models to plan procedures. Scientists simulated climate systems, molecules, and galaxies using graphical models, each of which used tools designed by software engineers. Today, 3D visualization is an indispensable tool in education, product design, and engineering. This universally shows how 3D graphics have become a core branch of software engineering, not just the entertainment technology it is often thought to be limited to. In recent years, we've seen an explosion of new techniques that push realism even further. Real-time ray tracing is now possible on consumer GPUs. Ray tracing better simulates how light bounces in a scene, producing reflections, shadows, and refractions with stunning realism. Physically based rendering, or PBR for short, ensures that materials such as metal, glass, or human skin appear physically accurate. New tools are being developed and iterated on every day to improve the technological ability to simulate the visual nature of the real world. When we look back, each breakthrough in 3D graphics reflects a parallel evolution in software engineering. The introduction of APIs like OpenGL demonstrates the power of abstraction and modular design. The move to shaders introduced the concept of distributed computation and parallelization, while game engines showcased reusability and scalable architecture. Even today, concepts like parallelism, optimization, and maintainable code bases remain at the center of high-performance rendering. In many ways, 3D graphics have served as a testing ground for some of the most advanced software design patterns, proof that visual computing and engineering rigor go hand in hand. Take a moment to reflect. I've heavily discussed the history of 3D graphics, but if 3D graphics continue advancing, what does that mean for the software interfaces themselves? Could your operating system, your web browser, or even your productivity tools evolve into immersive 3D spaces? Much of our digital lives remain in a 2D space. Does the future entail bringing those products into a 3D environment? Looking ahead, 3D graphics are merging with new technologies like spatial computing, augmented reality, and virtual reality. Software engineers are now building systems where digital and physical worlds overlap seamlessly. Cloud rendering allows complex spaces to be processed remotely and streamed to lightweight devices. And artificial intelligence is being used to auto-generate 3D environments, textures, and animation from text or 2D images. In closing, 3D graphics evolved through decades of software innovation from simple matrix math to photorealistic worlds. It's a journey that mirrors the progress of software engineering itself: abstraction, iteration, and creativity. Every rendered pixel represents not just the light and color, but also the collective brilliance of the generations of engineers turning code into art. Thank you for your time today. All graphics have been cited below, and any uncited graphics were made by me. Thank you for your time.